So, hello everyone. In the previous lecture, we had covered the basic circuit topology of MMC. In today's lecture, we will talk about the modeling, mathematical model of the converter, from which it will be possible for us to know about the voltage and current ratings of the arm of the converter and the IGBTs or the transistors, DC bus voltage on the capacitor, etc. So, the steady state model of the converter will be covered in today's class. In the last lecture, so we were talking about MMC, and then we talked about the drawback of CHB, from where we said that the MMC had a capacitor on the DC bus, and some of the features we discussed, and from where we said that the equivalent circuit of an MMC can be thought of as controllable voltage sources. I mean, there are 6 arms, and so these 6 arms act as 6 controllable voltage source. The operation is dependent on how we tweak this controllable voltage source. So, how well we modify the controllable voltage source, or we can alter the controllable voltage source. This controllable voltage source is made up of transistors inside the cells and having a capacitor as the DC bus. Okay. So, how well we change, modify, alter these controllable voltage sources, and that is how the operation of the converter can be controlled. So, we also said about this steady state equations, where we found out that the upper arm voltage has a expression like this, and the lower arm voltage has an expression of like this, okay, neglecting the inductor drop, which is a reasonably good approximation. So, from here we talked about this particular waveform, which is the waveform, for example, for AC to DC application. The equation which we had written earlier or in the previous slide now is diagrammatically represented here in this waveform, where these arrows, the red and the green arrows, represent the instantaneous voltage magnitude of the upper arm and the lower arm. So, these are the controllable voltage sources made up of these cells. So, we said that the converter can be, you can think of the converter both ways, like you can think of an AC source present, and then you want to produce a DC, which is the rectifier mode of operation, or if you have a DC and you want to produce a variable AC, then it becomes a inverter mode of operation. So, the same circuit remains, only the arrows flip their direction. Okay. I mean, at one point of time you can, we had discussed about it. Okay. So, it is also possible that the DC bus is less than the peak of the AC bus, AC voltage magnitude, and an extreme case we said about the short circuit in the DC bus. So, today first we will see what is the arm voltage, how much arm voltage needs to be produced from the converter, or how much is the blocking capacity of the arm. So, if we see the equation, and we will rewrite the equation here, we have seen this equation earlier. V u is E by 2 minus V m sin omega t, and V L is E by 2 plus V m sin omega t. V u is the upper controllable voltage source, this one, and VL is the lower controllable voltage source in any particular phase. Now, if Vm is less than equal to E by 2, this is the most common type of operation, like when you are, for example, converting from AC to DC, that is an HVDC. For HVDC application, Vm is usually less than equal to E by 2. So, if this is true and if you substitute it here, then you see that this E by 2 minus E by 2 sin omega t, and so we find that the VU voltage, it is between 0 and E. Okay. In a similar fashion, we can also see that the lower side voltage is between also 0 and E by substituting this Vm as E by 2 here. Okay. So, therefore, the voltage that needs to be produced by the upper and the lower arm is equal to the total DC link voltage. Okay. So, which means this arm here and this arm, the total voltage that needs to be produced by this arm as well as this arm is equal to the DC bus voltage. Okay. So, this E is the total DC bus voltage. Okay. So, the upper arm as well as the lower arm, the voltage that needs to be produced from them is capital E, or the total DC bus voltage. This is also understood from this this waveform here. Okay. It is also understood that suppose the AC voltage is reaching this place. So, let me draw it. If the AC voltage is something like this here, okay, if the AC voltage is something like this is the condition where Vm is equal to E by 2. Okay, this is the condition I have drawn. So, if Vm is equal to E by 2, you can see the length of, for example, the maximum length of this arrow, the maximum length of this arrow becomes this much. Okay. So, this is the length of the arrow. So, this is the maximum instantaneous voltage that the upper arm has to produce, right, and of course, this is also the voltage that a lower arm has to block, right. So, what is the length of this maximum arrow? The length of this is equal to E, because you see this is E by 2 and this is minus E by 2. So, therefore, this maximum length of the arrow is equal to E, and hence during this condition where Vm is equal to E by 2, then the voltage that needs to be produced is equal to E. So, that is what we have seen here, 0 less than equal to Vu less than equal to E. Now, so this means that the arm which is consisting of many number of cells, okay, suppose there are n number of cells or submodules, okay, in each arm, capital N, this capital N is the number of submodules or arms in any submodules or cells in any arm. If n capital N, then this whole E has to be supported by these n number of cells. So, the voltage rating of each cell, the voltage rating of the capacitor in each cell, as well as the voltage rating of the switch in each cell, all of them must be equal to E by N. That is what here shown here. Okay. This E by N here. Okay. So, the voltage rating of the cell, as well as since the voltage rating of cell is capital E by N. So, therefore, each cell has its own capacitor that must be rated for that much voltage E by N, and so because it is having say half bridge or full bridge, each transistor will also be rated for E by capital N. The voltage rating of the cell is dependent on how many submodules we choose in any arm. Okay. Now, here comes a choice. Okay. Here comes the choice, because you see, if you so suppose we are thinking about a HVDC line, HVDC converter, MMC acting as an HVDC rectifier. So, then for example, we can have the DC bus as say plus minus 200 kilovolt. That means, this capital E, which will be equal to 400 kilovolt. Okay. In that condition, how many number of cells or how, what is the value of n that we should choose? Of course, the first criteria that we should follow is what is the available rating or what is the available voltage rating of the transistor that we have. Now, we can choose 3300 volt IGBTs, we can choose 4500 volt IGBTs, even we can choose 6500 volt IGBTs also. These are usual values, but then exactly which IGBT to be chosen is not so straightforward. Okay. If you increase the voltage rating of the IGBT, then we will require less number of IGBTs, right, but it will increase the voltage rating on the switch and the capacitor. If you increase the number of submodules, then the voltage rating of the IGBT will go down. So, but then if you increase the number of submodules, then the cost, the complexity, because you have to control so many IGBTs together. So, say if you instead of 100 cells in each arm, if you increase it to 200 cells in each arm, of course, the voltage rating will go down, but now you have to, instead of 100 cells in each arm, we have to now control 200 cells in each arm, which increases the complexity, which increases the size, and also the controller, because the gate drive requirement, the fiber optic, the isolation requirement, many other things will be affected. So, this is not a very straightforward choice. Okay. So, even some manufacturers use the half bridge as like this. Some manufacturers even use half bridges like what we have discussed, like this as the half bridge, okay. But some manufacturers do not have a single IGBT here. Okay. They have something like this, there is no single IGBT, but a series connection of several IGBTs. Okay. So, some manufacturers have this. So, this one IGBT is not a single IGBT, but several series connected IGBT. Now, this cannot be directly said, okay. It needs to be simulated, and we have to find out what is the complexity, what is the loss. Remember, the loss is very much important, because we are having a large number of series connected devices. So, the conduction loss, okay, the conduction switching loss will not be so important here, because with so many cells in series, the output waveform is almost close to sine wave. Okay. So, we do not need very high switching frequency for individual cells, but the conduction loss is substantial, because whatever current is flowing, it is flowing through several cells in series, and all of them are coming in series. So, the on state voltage drop is kind of adding up this case. So, this high value of n increases the conduction losses in the converter. So, we have to kind of like see what is available in the market, how much expertise we have. Again, as I said earlier, we have more expertise on a 1200 volt IGBT rather than a 6500 volt IGBT. Okay. So, there we have to make a choice, like which IGBT, which rating IGBT we have more expertise, whose gate drive we know very precisely how it functions, how is the fault performance of such an IGBT, and many other factors come in, and then we can say that okay, by considering all these factors as well as the loss and many other dynamic performance, then we choose this value of capital N, how many cells. But the starting point of this calculation, it comes from the fact that the rating, the minimum rating of the voltage, the minimum voltage rating is capital E by N. So, this is the starting point of the design. Next is the current flowing through the arm. Okay. Now, this is a little bit tricky, okay. The arm current. Okay. Now, let me first tell you what does the arm current contain. So, primarily the arm current has a DC as well as an AC component. Okay. This feature of the converter, where the arm is containing both DC and AC, is what makes this converter unique, and sometimes it is difficult to fully appreciate the operation of this converter. So, the arm current has both DC and an AC component. Now, why? First of all, the question comes up, why there is a DC as well as an AC. So, if you see the circuit of the converter, okay. Now, this is the arm current. Okay. So, this IU here and this IL here. So, upper arm current and lower arm current. Of course, you can see here that the sum of IU and IL is what is making the load current here. This is the load current. Now, the voltage produced by this converter is almost like a sine wave. So, the load current for this converter, we can assume that it is almost like a perfect sine wave, okay, and can be represented by the equation I load equal to I max into sine omega t minus phi, or something like sinusoidal function we can write. And since this is fed from both the upper and the lower arm, of course, that means both the upper arm and the lower arm will contain a fraction of this load current, and that is evident from the Kirchhoff's current law. So, the IU and IL will have a fraction of the load current, and generally because of the balanced operation of the converter, the IU and IL, upper arm and the lower arm in each phase, contains half of the load current. This is understood from the symmetry and the balanced operation of the converter, that IU and IL contains half of the load current, and the load current can be safely assumed to be a purely sinusoidal current. So, the AC component of the IU and IL is understood pretty easily. Now, why is there a DC component? Okay. As I told you, IU and IL has not only an AC component, but also a DC component. Now, why DC? This is where this converter is unique. Okay. Why there is a DC component? Now, if you see how we have made this upper arm and lower arm, remember that the upper arm and lower arm, these two voltage sources, they are made up of capacitors. Capacitors are different from rectifier fed battery, because they do not have their inherent energy supply. Okay. They can temporarily store the energy, okay, in the form of half CV square, but they do not have a. So, these capacitors in the upper and the lower arm, they do not have a source of energy which is connected. Now, you see here this upper arm when the load current is flowing through the upper arm and the lower arm, of course, the real power, suppose we are taking it as a, let us take an example of a DC to AC converter. Okay. So, DC to AC converter. So, the real power is flowing from the DC bus into the AC load. Okay. This is how it is flowing to, this is the load here and this is the source here, DC source. From the source to the load it is flowing. Of course, it gets divided into the 3 phases. So, this gets divided into 3 phases and then it flows to the load 1/3, 1/3, 1/3. Now, this DC source is the source of energy and the source of, like, the real power is flowing from this DC source into the load via these capacitors. These are made up of capacitors, these are all made up of, these sources are capacitor. So, the real power is flowing from this DC source via these capacitors into the load. Okay. It is flowing like this via the capacitor. Now, when real power flows through the capacitors, what happens? This comes from the basic circuit understanding. When real power flows through capacitors, either the capacitor energy will go up or the capacitor energy will go down, depending on the direction of the power flow. So, either you will increase this half CV square or you will decrease the half CV square, because you are allowing the real power to flow through the capacitor. If reactive power flows through a capacitor, over a cycle we give some energy to the capacitor and get it back from the capacitor. So, over a cycle the net energy which is supplied or which is taken from the capacitor becomes 0 when there is a reactive power flow, that is the voltage and angle, voltage and current have a 90-degree angle. But when real power flows through a capacitor, then the energy of the capacitor will either go up or it will go down, unless we take some precautionary measure. Okay. Now, you see here, when the real power is flowing from this DC through the capacitor through the load. Okay. So, this arm which is made up of capacitors, several capacitors in series, the arm will lose its energy, okay, because or it will gain energy when the power is flowing from here to the load. So, in order that the energy in the arms is at a steady value, okay, it has to be at a steady value. Okay. Otherwise, what will happen? Why these arms are needed? Because they are creating this multi-level, or they are creating this sinusoidal voltage source, multi-level sinusoidal voltage source. They are very much needed, and it is important for us to keep the capacitor voltages to a fixed value. If the capacitor voltages are going up or going down, then we will not be so easily getting the sine wave output, right. If the capacitor voltages is diverging, we will have a non-sinusoidal output. This we have seen earlier also, that if the voltages are not kept at a particular value, if the capacitor voltage are not kept at a particular value. So, instead of a sine, so if you want to, because we are trying to create a sine wave from the arm voltage, and this is made up of like this. So, greater is the number of steps, closer is we are going to the sinusoidal waveform. So, this is what we are trying to achieve. So, this is the sine wave here, okay. But this will be possible only if these steps are kind of like steady steps over a period of time. These are very stiff steps. If the capacitor voltages are going up or down, these steps will no longer be very discrete steps. It will increase, decrease, or it will fluctuate like that. So, it is important that the capacitor voltage in these arms, they are at a particular value within, of course, we will have a tolerance. There can be a slight fluctuation in the capacitor voltage, but it should be within the acceptable limit. Only then we get this kind of like a stiff steps in the output waveform. So, it is important that the capacitors hold their voltage. Now, when this real power is flowing through the capacitors, it will not be able to hold that voltage, because the energy energy corresponding to this real power will cause the capacitor voltage to either go up or go down, depending on which direction the energy is flowing, based on the half CV square. So, therefore, the AC component of the current, the AC component which is flowing through here, this AC component must be compensated. It must be compensated. Compensated for what? So that the capacitors hold their voltage. Okay. So, the capacitors do not diverge, the voltage on the capacitors do not diverge either up or down. Okay. So, how can it be compensated? It can be compensated by a circulating current. It can be compensated, you can say, by a DC current. Okay. This is the DC current. Why it is DC, that we will come. Okay. I can mathematically we will show why it is a DC, but there must be a circulating current. Okay. This circulating current ensures that the net energy taken from this source over a certain period of time, the net energy is 0. So, we do not take or give any. So, this is 0 here. Okay. This circulating current is essential for the operation of the converter. Okay. Without the circulating current, the voltage on the arm will either go up or the voltages will go wayward. Okay. It will go very high or it will go very low, either to the DC bus or to 0. Okay. Because the real power is flowing through the arms, and we do not have a mechanism, because so the arm is losing the energy or gaining the energy, and we do not have a mechanism to compensate. That compensation mechanism is provided by the circulating current. Okay. We can find out how much is the circulating current, and it is predominantly DC. Okay. The circulating current is predominantly DC, because this circulating current is in fact the DC component is what makes sure that the energy is over a period of time is 0. So, let us now see. So, therefore, this statement arm current has both DC and AC, this can be understood from the operation of the converter. Okay. So, half of the load, so this is what we have written. If we neglect the capacitor voltage ripple, then half of load current will flow through the arms at the fundamental frequency. So, that is the load current frequency, and arm currents will have a DC to maintain the power balance or the energy balance. Okay. So, that the arm energy is fixed. However, in addition to this, there is a second harmonic voltage also that comes on the capacitors. Okay. So, the capacitor has a ripple, and this causes us, this is actually a second harmonic voltage ripple on the capacitor. This is not very high, this second harmonic voltage ripple is not very high, it has some second harmonic additional currents which flow through the converter, but it does not come on the DC side, neither it comes on the AC side. Okay. There is an additional second harmonic, we will talk about this additional second harmonic. Okay. The origin of this second harmonic can be understood from the fact that this voltage source here, this voltage source here, this one, This voltage source is a single phase voltage source and the single phase current is flowing. Note that these three voltage sources are completely independent of each other, they do not know about each other, they do not even know that okay, there is a lower arm. Okay. So, these are single phase 6 single phase voltage sources, and we know that when through a single phase voltage source a single phase current flows with a phase difference between them, then there the power which flows through this voltage source has a DC component and a second harmonic component. V I cos phi, if you multiply it, you will get one DC component and a 2 omega t 2 omega component. That second harmonic component in the power causes a second harmonic voltage fluctuation on the capacitor. So, that will cause some additional harmonic currents in this. We will talk about it, but we will talk about it sometime later. We will first talk about the DC component. The DC component is essential. The second harmonic component comes because of the power fluctuation.